The Monty Hall problem is one of the most famous problems in probability and has been discussed at length for decades. The Wikipedia article alone is over 20 pages long, and there have been dozens of papers published discussing it. This is perhaps a little surprising given how simple the problem is, based off of a television game show in the United States from the 1960s called Let's Make a Deal. You might wonder why it's worth talking about again. As happens often, especially in math, most of the discussion is caught up in the mechanics of the solution, how you calculate the answer. I think many people find this unsatisfying, and I think this problem is a wonderfully accessible avenue for exploring some deeper ideas, touching upon metaphysics and philosophy. In particular, studies have shown that over 90% of people get this problem wrong, including experts in probability. Additionally, many of those people, including experts, will ardently stick to the wrong answer even when shown the correct answer. And yet, the wrong answer they propose would have explosive implications about causality and the nature of time if it were to be true. Yet, people think it's intuitive. I think this happens because people get caught up in the mechanics of probability and lose sight of the fact that it's a formalism, an abstraction, and as the saying goes, the map is not the terrain. So come along with me and let's explore that terrain together. Let's go back. Imagine a game show. The host's name is Monty Hall and you're a contestant. You're presented with 3 doors and told that with equal probability, behind one door there is a prize, while behind each of the other 2 doors is just a goat. It's stipulated that the goats and prizes are never moved or switched. Then you're asked to choose a door. After you make your choice, Monty Hall opens one of the other 2 doors to reveal a goat, and then you're asked if you would like to change your mind and pick the other door Monty left closed, or instead, just stick with your original choice. For starters, it's clear to everyone that your first choice is random, with equal probability across the 3 doors, meaning initially you have a 1 in 3 chance of picking the door with a prize, and a 2 in 3 chance of picking a goat. The confusion comes next. Monty Hall opens a door to reveal a goat and asks if you want to change to the 3rd door or stay pat. Many people intuitively feel that you are now choosing between 2 doors, each of them still equally likely to have the prize, and therefore your chances are now 50-50. Since it's 50-50, they reason it doesn't matter whether you stay or switch. And while it is true that choosing randomly between 2 equally likely outcomes has 50-50 probabilities, in this situation, suggesting 50-50 odds has astonishing metaphysical implications that hardly anyone ever considers. Before the goat is revealed, everyone agrees the probability of your chosen door having the prize is 1/3. If we stopped right there, you would win the prize roughly 1 in 3 tries. This derives from what we call a frequentist interpretation of probability. When you pick a door, there either is a prize or a goat behind the door. I would just clarify that we're talking about classical goats and prizes, not some quantum Schrodinger entangled superposition of goats and prizes. In the quantum realm, you really could have both a goat and a prize behind your door right up until the moment you open it. But in the macro world where we live, there is either a goat or a prize behind your door. We just don't know until we open it. The 1/3 probability refers to the frequency at which you would get the prize if we repeated this over and over again. Now, consider carefully the implications of saying that the probability becomes 50-50 after Monty reveals a goat. Think about causality in the direction of time. Remember, in the macro world, once you make your choice, there is either a goat or a prize behind your door before Monty reveals anything. Saying that the probability goes from 1/3 to 50-50 after Monty reveals a goat implies that the act of him revealing a goat causes your goat to turn into the prize 1/6 of the time, or 1/2 minus 1/3, right? I mean, think about it. Monty doesn't touch your door or what's behind it, and we stipulated that nothing ever gets switched. You are totally happy that before Monty opens another door, you would get the prize 1/3 of the time. You're totally happy that once you pick your door, there either is or is not a prize behind it. And now you're proposing that Monty opens a different door to reveal a goat, you stick with your original door, and yet wind up getting a prize half the time. Like, nothing really changed for you, it's just Monty revealed a goat. This means that 1/6 of the time you chose a door that has a goat behind it, then Monty reveals a goat, and now somehow your door has a prize. Just sit on that for a moment. Somehow this implies that Monty revealing the goat causes you to go back in time and choose a different door, that an event in the future is causing, or at least influencing, an event in the past. Suddenly, what seemed like a very simple, intuitive answer has become a very bold, reality-shattering proposition. Now, that doesn't necessarily mean it's wrong, I mean, see quantum mechanics, but the claim has become much bigger than you probably thought. A simple answer about randomly picking between two doors just implied that events in the future are causally affecting events in the past. Let's do another thought experiment to tease this out a little. Imagine that after you picked your door, Monty opened two doors and revealed two goats. Wow, that's amazing! That means the probability of there being a prize behind your door is 100%. Hopefully this seems a little bit fishy. It should jump out that Monty can't reveal both goats unless you already picked the prize by chance. The causality violation is jumping up and down and waving a big red flag. Somehow, Monty revealing goats is going back in time and causing you to choose the prize like every single time. It might feel different than raising the probability from 1/3 to 50-50. However, the same principle is at work. I think the reason this happens is because people have some intuition about what is formally known as conditional probability, and that intuition leads them astray. We're going to talk about conditional probability in a sec, but I want you to try another thought experiment first. Clearly, the fact that Monty always reveals goats is causing some problems. So let's consider what happens if Monty's choice were random instead. What happens if Monty makes a random 50-50 choice between the other two doors? Maybe he flips a coin or something. So 1/3 of the time, your original door has the prize like always. Then he reveals a goat no matter what, doesn't matter which door he picks. The other 2/3 of the time, when you picked a goat to start with, that means there's one goat and the prize left. So half of those times he reveals a goat and half he reveals the prize. So that means there's a 1/3 chance for each. This should feel pretty natural. Half of 2/3 is 1/3, right? In this case, if Monty reveals a goat, then indeed your door and the third door have an equal probability of having the prize. The conditional probability actually is 50-50, but we'll come to that in a bit. But what if Monty now randomly reveals the prize? Clearly, in this case, the probability that your door has a prize is now 0. In fact, let's revisit our thought experiment where Monty opens both of the other doors. Except this time we don't insist he reveals two goats, he just reveals whatever they are, goat or prize. Hopefully it's obvious in this scenario that the probability of your door having the prize either goes to 0 because he revealed the prize, or goes to 100% because he revealed two goats. This is a little confounding. It feels like the probability can change, sort of. So let's go ahead and discuss conditional probability. Conditional probability is one of the foundational ideas in probability. It lets us talk about the probability of some event given that some other event has occurred. We can discuss and calculate what is the probability your door has a prize given that Monty revealed a goat. Very quickly, remember that probabilities of all possible outcomes, known as a sample space or omega, must add up to 1, and events are just sets of possible outcomes. Significantly, events can overlap. Multiple events can contain the same possible outcome. The conditional probability is actually quite simple. If we can say the actual outcome is certain to be an event B, what can we say about the probability of it also being an event A? We express this as the probability of A given B, written like this. In order for conditional probabilities to make sense, we need to normalize them. If Monty were to reveal two goats and we know for certain our door has a prize, intuitively we want that conditional probability to be 100%. By normalizing them, we can compare unconditional and conditional probabilities, even with different conditions, against each other. Notice, this makes the probability of B given B equal to 1, which should make sense. Also notice, we're essentially treating B as a new sample space. The probabilities in B add up to 1. The next part is an obvious thing they never tell you, but should help connect some dots later. Remember that in probability we're guaranteed an outcome? What this really means is that all probabilities are really conditional. The sample space is a set of possible outcomes, making it an event like any other, and an event with a probability of 1. What you think of as regular unconditional probabilities are just conditioned on the event something happened. So technically, they're conditioned on the sample space omega. Since we scale conditional probabilities by dividing by the probability of the event, we just divide by 1, so the numerical values are the same. And this might seem like a distinction without a difference, but we'll come back to it in a minute. We've laid the groundwork now to see why people get confused and want to violate causality. People get stuck thinking that probabilities change. But right now I want you to realize that unconditional and conditional probabilities for the same event can be different depending on the conditioning event. In other words, the probability of A can be less than, equal to, or greater than the probability of A given B. It just depends on the relationship between A and B. If we go back to the scenario where Monty opens both of the other doors, regardless, then we can state a few things clearly. The probability that you chose the prize originally is 1 in 3. The probability that you chose a prize given that Monty reveals 2 goats is 100%. The probability that you chose the prize given that Monty reveals 1 goat and the prize is 0. The original probability is 1/3 and never changes. It's just there are different scenarios with conditional probabilities that are different, some larger, some smaller. In the earlier scenario, where Monty randomly reveals just 1 goat, the conditional probability actually became 50-50. I believe this is why many people think the 50-50 proposition is plausible. Whether they know what conditional probability is or not, that's what they're thinking. But the fact that Monty's choice isn't random means it doesn't really work. So let's revisit our original scenario where he reveals 1 goat. Everybody is totally comfortable that the plain unconditional probability that you chose the door with the prize is 1/3. Remember that we said earlier that all probabilities can be thought of as being conditioned on the sample space omega, so P, you chose the prize given omega, is also 1/3. So what is the probability that you chose the door with a prize given that Monty reveals a goat? Well, what is the probability that he reveals a goat? He always reveals a goat no matter what, so the probability is just 1. Or P, Monty reveals 1 goat is equal to 1. The fact that it's 1 tells us something important. The probability of omega also equals 1, and with finite possible outcomes, this means these two sets have the same possible outcomes, which means they are the same set. The event, Monty reveals 1 goat, is the sample space omega. This gives us a mechanical explanation of why even the conditional probability that you chose a prize can't be 50-50 when Monty reveals a goat. The condition is just the sample space, so the conditional probability is the same as the unconditional probability. Since the door Monty opens with the goat has 0 chance to be the prize, we can then infer that the other door must have 2/3 probability of having the prize. You might be thinking, wait a minute, we just said that since the probability Monty reveals a goat is 100%, the conditional probabilities are the same as the unconditional probabilities, meaning that the other door always had a 2/3 chance of having the prize. Some of you might object. We don't even know which door the other door is until Monty reveals a goat, so it couldn't have any probability. Right now, we're saying Monty always reveals a goat, but we're not saying which door he opens. So we can meaningfully talk about the quote other door without saying which door specifically he opens, but we're still hitting on something important. The formalism of probability has no sense of time. Possible outcomes have no internal structure or timeline. They're all fait accompli. Yes, by the formalism of probability, the quote other door has the prize 2/3 of the time. But there's no sense of always, no sense of before or after. It just is. That's the way the sample space is configured. At long last, we've come to the crux of our conundrum. Traditional frequentist probability only operates in one sample space at a time. But having Monty open a door is a different experiment than having no Monty and just randomly choosing one of 3 doors. And these 2 experiments have different sample spaces. We can do a calculation and determine the probabilities in each sample space. But we don't have any metaphysical tools to compare the 2 sample spaces or understand what changed. We can see that the 1/3 probability originally held by the door Monty opens, whatever that means, kind of moves to the 3rd door. But how? Why? We know each door has either a goat or a prize before Monty does anything. We're not dealing with quantum superpositions here. Frequentist probability looks at what happens when we repeat an experiment over and over. What are the frequency of the outcomes? Clearly though, Monty's action is affecting the experiment he is in at that moment, and not future ones. So what is probability? Does it have any physical substance or existence? What is actually happening when Monty opens a door? Well, fortunately for us, the 18th century brought us Thomas Bayes, whose work would eventually lead to the Bayesian interpretation of probability. We will discuss that and how we can use it to bring some light to this conundrum in part 2 of this video. Thanks for watching, and if you like this video, why don't you give the like and subscribe buttons a probability of 1. Until next time, enjoy the simple things.